So in the previous lecture we have seen the resonance condition. I'm just revising all the things. Listen Sanjay, if it is LCR circuit, all right, and we have given the power supply V naught sine omega t, is it clear or not? This is LCR. The current in this circuit may be what? The IT may be I naught sine omega t plus minus phi. Is it clear or not? And the maximum power is the current. Suppose this is the Vrms of the power supply, this is the time domain current, and the current is Irms. So what is the current in this circuit? Is equal to Vrms. The Irms is equal to what? Say Vrms upon Z. In some book, the Irms simple is written by I and Vrms is written by V and it is Z. Are you getting or not? For this circuit, listen. The Z is the impedance, which is nothing but XC minus XL or XL minus XC whole square plus R square. The Z is equal to what? Say omega L minus 1 upon omega C and plus R square. Is it clear or not, Sanjay? Right. So the current in the circuit is reciprocal to the impedance, and this impedance of the circuit, of the series LCR circuit, depends upon the frequency. Do you understand or not? So you tell me, if the angular frequency, the frequency of this source is omega, which is approximately 0. So what will be the impedance of the circuit? You tell. 1 upon infinity. 1 upon 0. So it become infinity. So Z tending to infinity. Do you understand or not? Right. If the frequency of this generator or the AC source tending to infinity, then what is the Z? If it become infinity, yes, again it tend to infinity. What is the minimum? Listen, Z is equal to this square plus this square. So this is positive plus this is also positive. This is constant, but this is the variable. So for Z minimum, are you getting or not? Z minimum, for Z minimum, are you getting? The omega is equal to omega naught is equal to 1 upon root LC. What is the minimum value of the Z? They become equal, XL and XC become equal, and it is R. Do you understand this or not? So listen one thing. If you draw the graph of the impedance, this is the graph of the impedance and the angular frequency. If the frequency of the source supplies is 0, what is the impedance? The infinity. As the frequency of this power supplies is continuously increasing, the impedance become decreasing, and the omega naught at resonance frequency, the impedance of the circuit become minimum and it become equal to R. Is it clear or not? Further, if you increase the frequency of this power supply, right, the impedance will increase in this way. Is it clear? Sanjay? Right. Listen one more thing. Yes, if we draw the current versus frequency, right, current versus frequency. So if angular frequency is omega is equal to 0, what is the impedance? Say, the impedance is what? Say infinity. So what is the current? V upon Z. So the current tending to 0. When the impedance of the circuit is decreasing, so current is increasing. Is it clear or not? And when the impedance is minimum, the current in this circuit become maximum current. Is it clear or not? At which frequency? At resonance frequency, the current in the circuit become maximum. And if the frequency, if the increasing, the impedance increasing, but the current will decreasing. Is it clear or not? Sanjay, copy this. This is the frequency, resonance frequency, when the impedance is minimum and the current is maximum, right? Can you tell me what will be the maximum power transferred? At this frequency, the condition is of resonance and the transfer power is maximum. What is the maximum power? Say I max square into R. Is it clear or not? Right. So now I will introduce the concept of the half power frequencies. Half power frequencies. Half power frequencies. Right. What is the half power frequencies? You tell. Listen one thing. This is the frequencies omega naught when the power transfer is maximum. But if you consider, right, the frequencies for which the power is half of the maximum power. Listen one thing. Let omega is the frequency for which the power transfer is the half of the maximum power. So what is the power? Say I square into R. This is the power. So according to question, according to the concept, the power is half of the maximum power. Listen, what is the maximum power? It is I max square into R. Is it clear or not? So when the current flows in this circuit is I, so what will be the power dissipated? Say I square into R. Right, R will cancel out. So current will be equal to I max by root 2. Is it clear or not? So listen one thing. If maximum power, if the current in the circuit is I max, what is the power in the circuit dissipation? The maximum power. If current in the circuit is I max by root 2, are you getting or not? So power will be equal to what? Half of the maximum power. Is it clear or not? Sanjay, for the maximum current, the power is maximum. For if the current is less than, how much is the current? If the current in the circuit is I max by root 2, so for this current, here the maximum power is transferred, but at this two frequencies, the power is half of the maximum power. Therefore, these two frequencies are called half power frequencies. Is it clear or not? So how to find these two half power frequencies? Say from this, the I is equal to I max by root 2. Is it clear or not? What is the current? Current is V upon Z. And what is the maximum current? V upon R. You understand this thing or not? Right. So VV will cancel out, Z is equal to root 2R. Right. And Z is equal to what? Say XL minus XC whole square plus R square is equal to root 2 into R. Please copy this first. So if you make the square root both side, XL minus XC whole square plus R square is equal to 2R square. So XL minus XC whole square is equal to what? R square, right? XL minus XC is equal to plus minus R. All right. So in this circuit, the XL is nothing but say omega L minus omega C is equal to plus minus R. If you multiply omega square LC minus 1 is equal to plus minus RC into omega, LC L into C omega square plus minus RC into omega minus 1 is equal to 0. Do you understand this or not? So from this is the quadratic equation, right? And the quadratic equation, the values, the roots will be found minus b plus minus root b square minus 4ac upon 2a, right? So these two frequencies we are going to find, which are called the half power frequencies, right? So listen one thing. So omega is equal to what? Minus b mean the minus of this RC plus minus root b square R square C square minus 4 into A into C is the minus 1 upon 2 into A, 2 into LC. So plus this is the minus plus RC plus minus root R square C square plus 4 LC upon 2 LC. This is the omega. Is it clear or not? So how many values of the omega we are getting from here? The 4 values we are getting, right? But the frequency is the positive quantity. So I will take the omega 1 is nothing but minus RC plus root over RC square plus 4LC upon 2LC, and the omega 2 is RC plus root over R square C square 4LC upon 2 into LC. These are the two values of the omega 1 and omega 2, which are called the half power frequencies. Half power frequencies. Is it clear or not? Although from this we will get the four values, right? The remaining two values, suppose omega is written as minus RC minus root R square C square plus 4LC upon 2LC. So this is what's in negative, so we will ignore this. Sanjay, you are getting this thing or not? Also, if it is minus and it is plus, this value is also ignored. Are you getting or not? Right. Wait for a minute. If this is minus and this value is also ignored. So this value is also ignored. Only the two values which are omega 1 and omega 2, and these are the positive. The omega 1 is a small value, omega 2 is big value, bigger than this. So these are called the half power frequencies. Is it clear? Bandwidth I am asking you, right? The bandwidth of the LCR circuit, the bandwidth is nothing but the frequency difference. This area or this region from omega 1 to omega 2, this is called the bandwidth. Bandwidth is beta, is omega 2 minus omega 1. What is omega 2? This is omega 2 minus omega 1. RC plus root over R square C square plus 4LC upon 2LC minus, this is the minus RC plus root over R square C square plus 4LC divided by 2LC. When you will simplify, this root square term will cancel out and it become RC minus RC upon 2LC. So this is 2RC upon 2LC. So CC will cancel out. So R upon L is the bandwidth. This is the bandwidth, delta omega, right? Omega 2 minus omega 1 is the bandwidth of this circuit. Is it clear or not? Is the bandwidth. So it is clear from this expression. The bandwidth, what is the bandwidth? Listen one thing. At this frequency, the power dissipated is maximum from omega 1 to omega 2, right? The power is from half power dissipation to the maximum power. So this region is called the bandwidth, and the bandwidth is proportional to what? Say R. If R is decreasing, bandwidth what? Bandwidth is also decreasing. But what is the maximum current? Maximum current is V upon R. If R is reducing, the maximum current will increase. So if you draw the graph, listen one thing. This is the current versus frequency graph. Are you getting or not? So the graph, if you reduce the resistance, right? If you reduce the resistance, suppose this is the R1. So the circuit will be like this. The graph between the current and the frequency will be like this. Are you getting or not? Like this, right? Listen, this is the bandwidth for the R1. Are you getting or not? Suppose this is the R2 and this is the R3. For the R3, this is the bandwidth. Are you getting or not? So R3 is reducing, is less than R2 and R1. Is it clear, Sanjay, or not? You tell. As the resistance is decreasing, the peak current, the maximum current, this is the I1, and for this case the I2. So the maximum, this is the maximum current 2, this is the maximum current 1. Maximum current is increasing. Understood or not? This is the bandwidth 1, this is the bandwidth 3. So bandwidth 3 is less than the bandwidth 1. Understood or not? And the maximum current I max 3 is greater than I max 1. Is it clear or not? The quality factor, you tell me. The quality factor, which is defined by the Q, right? The quality factor is defined as the resonance frequency divided by bandwidth, right? What is the resonance frequency? Say 1 upon root LC, and bandwidth is R upon L. So Q is equal to 1 upon root LC, and this is L upon R. It is 1 upon R root L upon C. This is the quality factor. Are you getting or not? This is the definition. So as R is reducing, R is decreasing, quality factor is what? Increasing. Right. So if you consider the quality factor, so the quality factor is Q1 and quality factor is Q3 for this circuit. So R3 is less, but quality factor Q3 will be greater than the Q1. Because the bandwidth in this case is very small, right? So the quality factor will be more. Okay, so now I will discuss the choke coil. The concept of choke coil. The choke coil is nothing but the inductor with resistance connected in series, right? Suppose if it is a coil, right? Big coil, it is a big coil, right? It is made of the copper wire, so it has the resistance automatically. So this coil has the inductor as well as the resistance, and this system is nothing but is called the choke coil. When it is connected to the alternating source like this, right, you have to find the things, right, in this case. Are you getting or not? In the choke coil, once when it is connected to, right, connected to DC supply, DC supply. Are you getting or not? So when it is connected to DC supply, this choke coil is connected to DC supply, the inductor become a wire and only the resistance act over there. So in this case, the current is I1, this is V. So I1 is equal to V upon R. So from here, the resistance of the choke coil is found. This resistance is found. Is it clear or not? And if when resistance is found, the XL we know. When this choke coil is connected to the AC source, right? Suppose this is the V, this is the XL, this is the X, this is the R. So the current in this circuit is V upon Z is equal to V upon root over XL square plus R square. So in this way, the IRMS current we can find in the choke coil. Is it clear, Sanjay, or not, you tell? Let's copy this. First, it is connected to the connected in AC circuit and potential. What should be the potential? No, it is simple then. Connected to AC voltage sources of 130 volt is applied to the circuit. Potential difference across the resistance is what? Say 50 volt. What is the potential difference across the choke coil? If potential difference across the choke coil and a resistance, this is a choke coil. What is the potential then? Only the inductor is over there. So this is the VL. So the V is equal to nothing but VL square plus VR square root. So this is 130 is equal to VL square plus 50 square, right? So this is 130 square is equal to VL square plus 50 square. Is it clear or not? So VL square is equal to 130 square minus 50 square. So 180 into this is 80, the VL square. So the inductor voltage is 180 into 50. 18 पंजे 90 into 100, right? So this is 30 root 10 volt is the inductive voltage. Is it clear or not? Yes. So because the same student in your city from the Chennai, they ask me the question on the parallel LCR circuit, right? The LN branch. Okay, so now the parallel LCR circuit is also the important. The parallel LCR circuit, suppose this is the L, this is the C, and this is the R. Are you getting or not? If this is the voltage source, V naught sine omega t, is it clear? This is the VT. This is the current will go, this is the IT, this is the IL, this is the IC, this is the IR. All three are connected in parallel. All right. All three are connected in parallel. Right. So listen one more thing. If you make the phasor diagram to find the total current, how to find? All are connected in parallel, so the voltage V of the power source we assume to be V, right? So the current in the inductor will be lagging to the voltage, and the current in the capacitor will be leading, and this is the resistance current. Are you getting or not? Assume, for example, the IC is greater than IL for some time. This is the IL. So what is the phasor diagram? So it will be equal to what? IC minus IL, and this is IR. The total current is what? Say I, and the total voltage is V, and this is phi. Are you getting or not? So in this case, current is what? Therefore, current is leading. Current is leading by phase phi. Are you getting or not? So if current is leading, then the current function I can write I naught sine omega t plus phi, where the phi we have to find. Understand or not? Yes, Sanjay. The total current is nothing but the square root of IL IC minus IL whole square plus IR square. This is the IR. This is the IR, right? A square plus B square is equal to C square. What is the IC? This is one thing. If this is the XL, this is the XC, this is the R. What is the IL? Say V upon XL. What is the IC? Say V upon XC. What is the IR? Say V upon R. Right. So I will put the value V upon XC minus V upon XL whole square plus V upon R whole square. You will take the V common, XC minus XL whole square 1 upon R whole square, and this is the total I. The I upon V is nothing but 1 upon Z is equal to root over 1 upon XC minus 1 upon XL whole square plus 1 upon R whole square. So this is the value of the 1 upon Z. Are you getting? So it is 1 upon Z, right? So how can I write the total current? The current in the circuit can be written as I2 is equal to what? V naught upon Z. Listen one more thing. If you make the impedance triangle for this, right? This is suppose IR, this is IL minus IC minus IL, and this is the total I, and this is the phi. Are you getting? This is what? Say V upon XC minus V upon XL. This is V upon R, and this is V upon Z. So it is better to have the circuit. This is 1 upon R, right? 1 upon R. This is 1 upon XC minus 1 upon XL, and this is the 1 upon Z. This is the phi. So from here, the tan phi is nothing but 1 upon XC minus 1 upon XL upon 1 upon R. From here, the phi we can get, right? From here we can get Z. So what is the peak current? Say V naught upon Z, and this is the value of Z. So the current in this circuit can be written as how much? It is I naught sine omega t plus phi, and I naught is V naught upon Z. Z value is given by equation number 1, and sine omega t plus phi. What is the phi value? The phi value is tan inverse 1 upon xc minus 1 upon xl upon 1 upon r. Right? I am not writing the value of z, it is because very lengthy. So in this way the current in the circuit you can find in the parallel LCR circuit. Right? Copy this. Listen, one more thing. What is the current in the inductor in this case? Can you tell me? The inductor current is lag behind the voltage. So if this is the I naught, right, sine omega t minus pi by 2, or what is the I naught, the inductive current, say the V naught upon XL. In the same way, the current in the capacitor is I naught sine omega t plus pi by 2. The current in the capacitor is leading by phase pi by 2. And what is the I naught in this case? V naught upon XC. But the current in the resistance is I naught sine omega t in the same phase. And I naught you will write V naught upon R. Right? Because the peak voltage for every element is same. This is the V naught. So the peak current we can find with the help of this expression. Right? So this is the current in the inductor as a function of time t. Is it clear or not? So they may ask anything. Copy this. This is the parallel LCR circuit, and again, right. Okay, so in the parallel LCR circuit, there will be the same condition for the resonance, right? This current and the voltage will be in the same phase. Then the maximum power is transferred, and it happens when only when the current IC, right? This is the, suppose this is the IC and this is the IL, right? And this is the IR and this is the V, right? So the condition of resonance also occur in this parallel circuit. The IC and IL both are equal, so that the total current is nothing but equal to R in the same phase, of that of voltage, right? That of voltage. Are you getting or not? When the IL and IC are equal, so this is the maximum current will be equal to IR. This is the maximum current over here. So the maximum current is over there, then the condition is of resonance. IC and IL both are equal. So IC and IL both are equal. V upon X is equal to V upon XL. V upon XL. XC is equal to XL mean. Omega is equal to 1 upon root LC. So this frequency is called the resonance frequency as usual. Resonance frequency. Is it clear or not? Copy this. So complete this, the parallel LCR circuit. Now the last topic of this chapter we are going to discuss, that is the LC oscillation. Right? Okay. Now we are going to discuss the LC oscillation. Right? The LC oscillation, the last topic of this chapter, LC oscillation. What is the LC oscillation, you tell? Listen one thing. Suppose this is the capacitor. This is the capacitor and it is connected to the voltage of V naught, right? So what is the maximum charge on the capacitor? When it is fully charged, the Q naught is equal to C into V naught. Are you getting or not? Now this capacitor is disconnected. Capacitor is disconnected. All right, and connected to the inductor, unmagnetized inductor, an inductor, right? An inductor. So what will happen if this capacitor is fully charged? Q naught is the charge and there is an inductor, right? This is the key and it is open. At t is equal to 0, the key K is closed. Key K is closed. Are you getting or not? When the key is closed, the charge will start flowing in it, and after time t, charge on capacitor, charge on capacitor is suppose q, and the current flowing in the circuit is it. Are you getting or not? So initially at t is equal to 0, the charge is q, and after some time when the key is closed, at time t is equal to t, the charge on the capacitor remains q, right? It is pressed, and therefore the current start flowing in it like this. This is the current flowing in it. Are you getting or not? Since the charge is decreasing on the capacitor, so current will be written as minus dq upon dt. Is it clear or not, Sanjay? Copy this. Now we can simplify, or we can calculate the current of the charge in the circuit. Right, listen one thing. When they are connected, so VL, and this is the VL and this is the VC, both are equal, right? VL is equal to what? L di upon dt. And what is the VC? Say Q by C, because Q is equal to C into VC, Q by C. Are you getting or not? So if you differentiate once again, so this is d square it and 1 upon C dq upon dt. Are you getting or not? Multiply by this d square I upon dt square, right? Listen one thing, it is better to write I is what? Say I is minus dq upon dt. So L upon dt, what is the current? So minus dq upon dt is equal to q by C, right? So if you multiply L, d square q upon dt square is equal to q by C. Is it clear or not? So this is d square upon dt square is equal to minus q upon LC. When this quantity comes this side, this is 1 upon LC into q. Is it clear or not? So this is the second order differential equation of SHM. This is second order differential equation, second order differential equation of SHM. Is it clear or not? So we can compare d square upon dt square plus 1 upon root LC whole square q with the d square q upon dt square plus omega square into q. This is the SHM equation, and its solution is given by q is equal to q naught sine omega t plus phi. Is it clear or not? What is omega? Where this is the equation of SHM, the omega square, omega, where what is omega is the angular frequency is equal to 1 upon root LC of the SHM. So this is the charge as a function of time t, right? The q node is the maximum charge, and the omega is the angular frequency, phi is the phase difference, right? And these quantity we have to find. Yes, copy this first. At t is equal to 0, what is the charge? Say maximum charge. So q node is equal to q naught sine 0 plus phi at t is equal to 0. Are you getting or not? So this is 1 is equal to sine phi, and it is equal to what? Sine pi by 2 is equal to sine phi. So what is the phi? Say phi by 2. Therefore the charge as a function of time t may be written as the q naught sine omega t plus phi. Phi mean it is pi by 2. So q naught cos omega t. Is it clear or not? And the maximum charge is nothing but equal to CV naught if it is given in the question. Once you found the charge on the capacitor, you can also find the current in the capacitor, current in the branch. It is equal to minus dq upon dt, minus d upon dt, and this is q naught cos omega t. So the current is what? If you differentiate this, minus omega sine omega t. So this is q naught into omega, the current is sine omega t. Is it clear or not? This is the maximum current you may write, right? This is the maximum current, sin omega t, and this is the current as a function of time t in the circuit. So this is the sinusoidal variation. The charge on the capacitor is also sinusoidal variation. Is it clear or not? Copy this. Okay, so now in the LCR circuit, in the L and C and LC circuit, right? The capacitor is discharge initial, right? You can see, you can observe the current and the charge. What is the charge? Right, the charge is nothing but like this, right? At t is equal to 0, at t is equal to t by 4, this is t by 2, this is 3t by 4, and this is the total time. In the same way, if you consider the current, right, the current is like this, then like this. This is the current at t is equal to t by 4, t by 2, right, 3t by 4, and this is the t. This is the charge cos omega t. Are you getting or not? This is the current is equal to I naught sin omega t. When at t is equal to 0, the charge is maximum. When the t is equal to 0, charge is maximum and the current is minimum. As the charge is decreasing, the current is become maximum, right, and so on. Is it clear or not? Listen, one more thing. If you want to find the energy, what is the energy? Energy in the inductor, energy first in capacitor. What is the energy of the capacitor? Is equal to half C V square or Q square upon 2C. Since, listen one thing, since 1 upon 2C, the charge on the capacitor is as a function of time t, so the energy of the capacitor is also equal to the function of time t. So the capacitor energy as a function of time t is q naught square upon 2c cos square omega t. In the same way, the energy in the inductor, understood? The energy in the inductor is half L I square. So half L I naught sin omega t whole square. So energy in the inductor as a function of time t, half L I naught square sin square omega t. This is the inductive energy, this is the capacitor energy. Is it clear or not? Right. Listen, one more thing. The maximum energy half Li node square. What is the I node? Yes. Whew. What is the I node? Half L. What is the peak current? Did you remember Q node into omega was the peak current? So this is equal to half L Q node square into omega square. Is it clear or not? And what is the omega? The omega here I told you 1 upon root LC. So its square is equal to half L Q naught square 1 upon LC. LL will cancel out. So Q naught square upon 2C. Listen, this is the maximum energy in the inductor, which is nothing but equal to the Q naught square upon 2C. Do you understand this thing? The maximum energy of the inductor is nothing but equal to the maximum energy of the capacitor. Look, if you see, the energy in the capacitor and the energy in the inductors are periodically varying according to cos square omega t and the sin square omega t. Since the charge and the current in the inductor also varying the sinusoidally with time, that is why the energy stored in the inductor and the capacitor is also varying periodically. All right, copy this first. In the inductor and in the capacitor, if you make the graph of the energy, right, in the capacitor, t is equal to 0, the energy is maximum. You can check from here. If you make the graph of the energy in the capacitor, so the energy in the capacitor is like this. Are you getting or not? At t is equal to 0, this is t is equal to T by 4, right? This is T by 8, I think, because 2 pi by T into T by 8. So this is T by 4. This is the T by 4. The energy becomes 0 at T by 4 because T by 4 pi by 2, yes. And in the, this is the energy variation of the capacitor, capacitor, and this is the energy variation in the inductor. This is the energy of the capacitor as a function of time t, which is equal to, this is the maximum energy, right? And this is the energy variation of inductor as a function of time t. Is it clear or not? Half Li node square is equal to Q node square by 2. What is the meaning of the LC oscillation, you tell? The meaning of the LC oscillation is that the energy of the capacitor is transferred to the inductor, and in the next cycle the energy of the inductor is transferred to the capacitor. Then capacitor energy is transferred to the inductor, then inductor energy is transferred to the capacitor. Are you getting or not? So the energy in the capacitor and inductors oscillate, right? Energy of capacitor in the form of electrostatic field, right? Energy of the capacitor is transferred into inductor, and next, and again the energy stored in the inductor is transferred into the capacitor. So this is the oscillation of energy from capacitor to inductor, inductor to capacitor, and with frequency. What is the frequency of oscillation? Say 1 upon root LC. This is the frequency of oscillation of energy. What is the frequency of energy oscillation? 1 upon root LC. And this is called the LC oscillation. The LC oscillation means when the capacitor is charged fully and connected to the inductor, the energy is transferred to the inductor to capacitor, capacitor to inductor with same frequency, and this is called the LC oscillation. Is it clear or not? Copy this.